But that part is a little more complicated. We have to consider 3 factors for that flow. The first one, the disease spread because the contact between the infected people and the susceptible people. There are 3 types of contacts. Susceptible to susceptible, nothing happened. Infected, contact infected, nothing happened. But only when the infected contact to susceptible, then you do have the disease may spread. So to make it easy, we assume each infected person see many contacts per day. So since the total population of the infected is I, then every day there are this many contacts, C times I. Well, not all contaction between the susceptible and infected to make the disease spread. Somebody may not get contagious. So the second number is the probability that contacting is a susceptible person. And also we look at the probability that given a contact, the susceptible person really became sick. So there's another 2 probability we need to think. So as I said, there's 3 types of contacts. There's only a portion of the contacts you really happened between the susceptible and the infected. So give one infected person, the probability the contacted person is susceptible equal the total population multiply the total of the susceptible. So this equals the product of number of susceptible divided by the total of population. So why minus 1? Well, we minus 1 because nobody contacted himself. If you have a contact, you have to have 2 people to the other people. So that's a simple probability. Again, I said not all contact between susceptible and infected will transfer the disease. We only assume the probability like V could be 10%, 20%, depends how contagious is the disease. Like a flu is very contagious, like AIDS, the probability is very small. So put all the 3 factors together. Again, we consider each infected person, they have a probability to change the CFV times S, many person, from the susceptible to the infected in every day. See, C is how many contact this individual contact other people. F is the fraction the other people is susceptible. And the V is the probability when you contact the susceptible, it truly transfer the disease. And then you multiply S, that's how many susceptible are there. And okay, once you get this part, you remember we totaler has I many infected people. So the total change, we need to still multiply this I. Okay, now CFV are the parameters. They usually assume as a constant. the S is a susceptible population. That's a function of T. And I is a function of T, the infected people. So this component give you the change rate of the susceptible, which is CFVSI. And actually, we should put it negative because this is flow out. Yes. And that's the flow out here. So last, let's consider the change of infected. Well, the change of infected has a flow in from the susceptible and the flow out to the recovered. Then the gain is from what the S has lost. And the loss is what the R gains. So it's clear the change rate of the infected equals the gain from the S lost, that's ds dt, subtract the loss, which is the R gain. So you look back here again, and this equals di dt equals this part minus this part. That's very clear. So this part is ds dt, and the recovered is dr dt. So the third equation simply comes from the first and the second. If we substitute, ds dt is right here, dr dt is the first one we talked, is right here. So we get the third differential equation. Now, let's pause for a minute. For this baseline, you definitely need to look at all the details and trace back to the assumption. If you understand this baseline model, you have a chance to understand all the complicated one, like the SARS model we are going to discuss later. And there's a whole different modification, depends on the disease. In the baseline, now our analysis ends up with this system. The change rate of susceptible equals this constant CFV put together has a name. We call it the infection rate. The infection rate, you can call it B if you want. And the negative, because this is flow out. And dr dt is the Ri, that's how quickly, depends on how many people are infected, how quickly the people recover. And then dr dt, di dt, the change rate of the infected equals flow in from the susceptible minus flow out to the recovered. So what kind of equation is this? Well, if you recall what we learned in last time, the prey and the predator model, you see there's a big similarity. There are system equations, they are non-linear. Why non-linear? Because the S times I is a second order, a second degree. Second degree. And then we have these initial conditions. In the beginning, let's assume you observe when the disease has already broke out for a little while, then you know in the beginning, you observe how many people are potentially susceptible, how many people already infected, and how many people recovered. So the mathematics model, we typically call it the initial value problem. You remember that? Initial value problem. In short, we call it IVP. Since this is nonlinear system equation, we don't teach the undergraduate student to solve it analytically. I doubt even we can solve it analytically. So the best way to solve it is by using numerical solution. So let's look at the numerical solution. When we use numerical solution, we need to give a particular number. That's why it's called the numerical. So in that particular example, let's assume in the beginning, one particular disease, the health board reported. In the community, there's 20,000 of people could be contagious to the disease. So we call initial susceptible to 20,000. And we may estimate 1,000 people have already infected, and 500 recovered. That's how we start the simulation. And to figure out all those constants, you remember the constant have C, F, V, which we call it infection rate, and R, which is the recovery rate. Let's assume every day an infected person could have one contact with somebody else, to make it simple. And the probability to transfer the disease is 0.3, that's 30%. That's all you need. And how about the F? Well, the F really depends how many people are susceptible and what are the total population in the community. So this F is going to be 1 out of 20, remember minus 1, the total population minus 1, because you're doing the contact to yourself. So it's the probability the infected people contact as susceptible. So in this case, you'll find that this is 20,000 add 1,000 add 500 minus 1 make this many. That's the F. But the R is relatively easy. If you take 10 days to recover for average person, then the daily recovery rate R equals 1/10. That's relatively easy. Okay, put all those together, and this is the infected rate, and this is the recovered rate, and all we need is to replace the 3 constants and 4 constants in the mathematics model to this model. Now it's possible to solve numerically. You got the 3 equations and the 3 unknown functions with the initial value problem. So that concludes the mathematics modeling. So what we are going to do next is use Stellar to get the numerical solution and simulate the behavior of this disease spread problem.